All right, shall we get started? So welcome to EAS205, Applications of Scientific Computation. I think that maybe a more appropriate name would be Applied Linear Algebra course. As we speak, I'm recording it, and I'll be putting it on YouTube. For if you like miss a lecture or something, then you can always catch up with that. Have you seen the lectures from last year on YouTube? Anybody looked at that? So there are already lectures I recorded last year from the same course. So don't be confused. That's the 2013 version. Make sure to go to the 2014 one. So far there is nothing, but I will as soon as we are done with it, I will save it and record it and post it on YouTube. So for your reference. Okay. All right. So yeah, Tintin gave you last week 45-minute crash course into Matlab, right? Which covered pretty much almost everything you will need to know from Matlab for this course. It was a little bit too fast as I watched it on YouTube. It's also recorded. But that's the advantage of it's having there. You can go through it again and you can try to do some of the examples by yourselves. So today we will first go over the organizational matters, like where are we meeting, what's the grading gonna be like, what's the course about, and so on. And then we will start with some actual meat of the course, starting with like the simple things, notations, and basic vector operations. All right, so you already figured out that we are meeting on Mondays and Wednesdays, 4:30 to 6. It's pretty late, but that's what it ended up being. This maybe will move. That's no longer true. I put it there yesterday because I was trying to accommodate a few more people who still wanted to sign up. Last year I had like much smaller class, or something like 15 people, and this year for some reason lots of you signed up, which I'm very grateful for, which is great. I was even worried at some point that I might need like a bigger lecture room, but it seems that we will be able to all fit in here. There are still some free spots. It mostly matters for the midterms and the final exam because there will be like a test in the class. We will get there. All right, so I'm your instructor. My name is Ladislav Kavan. It's my official email, and my office is not too far from here in the Levine Hall. We are still working on scheduling all the office hours and so on, so the schedule is still a little bit in flux, but stay tuned. There is a website which has been updated recently. If you haven't noticed yet, let's see. Maybe here. The website doesn't have a lot of stuff, but what it has are links to all the relevant sites. So that's basically the information I just told you. Here is a link to my website in case you are interested in what I do, and here is the link to the YouTube playlist where I will start putting the videos as they are done. We will get to Canvas and Piazza and the Matlab licenses in a little bit. So I will keep this around and I will refer to it as we need. Okay. So that's for introducing myself. Now I have troubles remembering people's names, and there's lots of you, and I would like to know you. Is it too crazy to think about like name tags? Do you do that at some classes? I know that the Wharton students do that. Huh?
Yeah, the only people I know who do that are Whartonites.
Okay, so do you think it's too crazy? Do you not want to do that? Because I don't think I would have the mental capacity to remember all of your names until the end of the semester. Could you like maybe improvise, just like take a piece of paper and write your name? Would that be okay? Some of you I know, but most of you I don't, and I would like to get you know better. You might still be around for a while. Yeah, so thanks. That's absolutely perfect. You can just improvise name tags and use them for at least the few first classes, and I will try to remember who is who. That would be great. As we are introducing people, I have to introduce you some other very important people who are our TAs. So there is Yu Bang. Yu Bang is my, do you want to say something? He's my second year PhD student. He's done lots of work relevant to linear algebra. Some of his research projects are directly using it. We just had a discussion about matrix stuff and how to optimize some solving large linear systems. So he is very much on top of the ball. And Doron is also here as another TA. Just one of the best students last year at this course. So I'm very delighted to have them on board. There is a third one, Kritika. This is the cool thing, by the way, about this. I can just like point things and annotate things. So Kritika is the third TA. She couldn't make it today because she has a conflict. She might come on Monday to just say hello. And maybe since there is so many of us, in case we just can't handle or the load of correcting your amazing assignments and everything, then maybe I'll also ask Tintin, who you already met last week. He was doing the Matlab recitation. He's my third year PhD student. And all of these guys, they will of course have office hours as you are used to, but again, give us a little bit to work on that. Yeah, thanks for the name tags. That's helpful. I'm not sure if I'll be still able to remember all of you, but we will see about that. Yeah, so if you guys want to stay here, you are welcome to. If you want to run away to do your thing, that's also fine. I guess I will still go over some organizational things, so that's up to you. Okay. So let's do the high-level course goal. So it's all about linear algebra, and there are some other courses about linear algebra which you can take here too. Some are from the math department. And there are different ways you can approach linear algebra. And in this course, we are approaching it from the very applied point of view. So linear algebra is a part of mathematics, and in theory you could all build it like axiomatically, right? You probably had it in some mathematical logic and so on, that you can sort of start from some small set of basic axioms, and then just using logical principles, logical rules, you derive theorems, which are then your pieces of knowledge about the theory. And you can build linear algebra just like that. And we will do a little bit of that, but we will. This is not a math class. If you want like a math course like this, that's how my linear algebra course was when I took it more than 10, well, maybe actually like 15 years ago. And I hated it because I didn't know what was going on. I thought here is some sort of linear spaces, and here are some vectors and so on, and here are the rules, how it works. But I didn't really see what it's good for and how would you possibly use it to do something practical. And the whole point of linear algebra, the whole point why we are learning it today, and we'll be learning it for the rest of the semester, is that it has a lot of very cool applications. And I will go over some application domains soon. But my point here is that I want to give you a linear algebra from scientific computation perspective. So really looking at some specific problems which we can solve using linear algebra, and there is a lot of them. And that's why we also have Matlab in place, so you get your hands dirty with some actual matrices. In the math classes, there's a vector, matrix, sure, but usually you don't really get to touch any actual data, any actual matrices with some actual numbers. You sort of only reason on the theoretical level about things, which I think is missing the beauty of it, because thanks to computers, you can really put these things to work. It's not just theories, which the theories are also beautiful, but you can really put it to work. Where is the second bullet to it? That's basically what I was talking about. So linear algebra is a cool piece of mathematical theory. It's one of the basic math theories out there. If we will touch a little bit on group theory, which is like if you will, like nonlinear algebra, which starts getting a little bit more hairy. You probably have some classes on calculus and so on. That's like another example of that, right? And the beauty about linear algebra is that it can be used to solve a wide range of problems, not just in computer science, but also in engineering. I'm not sure what are your backgrounds. When I last looked at the list, was all sorts of varied backgrounds, right? How many of you is from computer science? Okay, it's a decent amount. and from other like electrical engineering, somebody, or some non-computer science background? You're mechanical? Yeah, right. Some other? So linear algebra is really basics for many things. Let me go through a few problem areas where there are immediate applications of linear algebra. This is my favorite graphics. That's my personal background. If you go to my website, which is linked from the main course website, you will see some work I've been doing. So the core graphics problem is to compute lighting in a scene, right? Imagine a scene like this classroom. I have some light sources. There would be one, right? There would be some more complicated light source there. There would be some light entering through the windows. And the task is to compute the actual lighting in the room. So how much light will like fall here or somewhere else, right? And linear algebra is very suitable for that because light behaves linearly. If I shine the two light bulbs on the same thing, the total light just adds together. So light transport behaves linearly. You can directly apply it for rendering. There's other areas of graphics where linear algebra immediately is applicable. Surface modeling, splines, subdivision surfaces. So the idea is, I don't know if some of you do know that, some of you who do graphics, but if you are doing some sort of virtual characters or things like that, you probably imagine that they are like continuous surfaces in the world, but what the artists only specify, they only specify some coarse piecewise linear approximation of it. And what these splines and subdivision surfaces are about, they are about creating smooth surfaces out of piecewise linear, typically polygonal approximation. So this would be like an example of an approximating spline. So what an artist would draw would be something like this, so just like four vertices connected by lines, and the spline essentially smoothes it out. If you know like Pixar movies, for example, the Avatar, that's like already a little bit advanced, but Pixar uses subdivision surfaces a lot. That's why you see all these nice smooth characters. And sometimes there are some special tricks how to control like sharp features. If you remember Toy Story 3, the tip of the nose of Woody had like a discontinuity, which you can explicitly model. And the splines and subdivision surfaces, they come directly from linear algebra. You can express it all using matrices. So that's something that our course will be immediately used for. Actually, one of the projects I think will be on splines. So you will get to see, so you will actually get to work on some basic version of that. Not quite the Avatar level yet, but you will get to see the idea. Robotics, some of you from robotics background? Yeah, not a whole lot. So kinematics and dynamics of robots, that's where we sort of start leaving the nice linear playground, because already kinematics is quite nonlinear. But what do we do if we have to deal with some nonlinear problems is that we linearize things. So the moment you take derivatives and you move to velocities, you convert the problems to linear problems. And that's also the case of dynamics of robots. And the whole apparatus of linear algebra immediately starts being applicable there. That's how you basically usually approach nonlinear problems, because the linear algebra is so powerful that it turns out that quite often the most efficient way to approach nonlinear problems is to locally linearize, solve some local linear systems, do some small step, move somewhere else, and rinse and repeat. Linearize, do some small step. That's how Newton's method works, for example. I'm just giving you an overview. If it's not making sense, that's okay. If you have some questions, that's also okay to ask, always, of course. Here is another cool application of linear algebra, transform coding. I really like that when I was learning these things. That's about image and audio compression. Again, one of our projects will be on exactly this topic. Do you know the JPEG, MPEG standards? I mean, you certainly do. All the images are encoded in that standard, but do you know how they work internally? What's the main idea? The main idea turns out to be very closely related to the concept of orthogonal bases, which we will be discussing here. And the thing is that if you choose your bases in a smart way, and that's basically what the discrete cosine transformation of JPEG and MPEG, or even the wavelet transformation is about, then it turns out that your signal, for example, an audio signal, will be representable by just a fewer coordinates, that you can discard big part of the dimensions of the signal without really sacrificing a lot of the quality. So here is some illustrations of the wavelet transformation. This is again something that has implications in robotics. In general, it goes towards control theory. So control theory is about essentially making some physical systems do what you want to do. I guess the simplest example is like in a car. If you have cruise control, you just set the desired speed, and the system tries to figure out when it should brake and when the engine when it should put more fuel to the engine to achieve the desired speed. So this is about control theory. Again, boils down to problems in linear algebra. Another area which I don't have a picture about because it's a little more abstract, but it might be actually even the coolest one these days, is statistics and analysis of large data. Living in the age of data, you might have heard the big data buzzword, which is very popular these days. And again, techniques from linear algebra are used to analyze large amounts of data. Probably the most famous example of it is the PageRank algorithm. You know the PageRank algorithm? Do you know where it's used? Google, that was like their initial idea, I guess. Like now, like Google is everything, and it's infinitely more complicated. But the PageRank was a paper by Larry Page, one of the Google co-founders. And the idea is to use eigenvalue decomposition to find out which websites are most relevant. We will talk about this on one of the later classes, and I think you will also have a project on PageRank, like a mini Google type of project. PCA is a somewhat related idea to that. Do you know PCA, principal component analysis? Closely related to SVD, singular value decomposition. SVD is like essentially the sledgehammer of linear algebra. This will be the pinnacle of this course. We will eventually build up to SVD, singular value decomposition, which is like you can think about it as the most powerful theorem of linear algebra, which is related to principal component analysis. And what that essentially means is that if you have some data which can be multidimensional data, some sort of, let's say that just points in 2D plane, that what PCA does, it discovers the directions of principal variation. So in this direction, the data seem to vary the most. So this would be the principal component. That's just like a brief introduction to the idea. We will, of course, study it in more detail. All right, so this was just like a 10,000 foot or maybe 30,000 foot overview of some of the application areas. Let me also clarify what the course is not about so that you are not disappointed. And I talked to some people, EAS205, oh yeah, the Matlab course. Well, yes, it is a Matlab course, and no, it's not a Matlab course. The Matlab is, for us, it's a tool. I think Tintin already mentioned that. It's a tool, it's not the goal, right? For us, it's the tool to explore all the beauty of the applications of linear algebra, because Matlab, it's just the simplest way where you can bring all these theories to life, where you can really like create some even pretty large matrices and actually play with them, do cool things with them. You can compute your mini Google completely in Matlab, and Matlab is a nice GUI, graphical user interface, for the solver, for the linear algebra solvers, which we'll be discussing. And by nice, it means it's easy to use. You can, of course, do all these things in any other programming languages. If you know C++, if you know Python or Java or whatever you prefer to use, you can totally do it. But I guess that Matlab is probably going to be easier to use. That said, if you really want to use some different programming language for your homeworks and assignments, I will get to those in a second. You are welcome to do that. That was, maybe I can skip already to a little bit more about Matlab. Just I guess Tintin already mentioned it. Let me just say this quickly, that Matlab is a shortcut from Matrix Laboratory and has been designed for exactly these type of things, which we'll be doing for our projects here. And what I wanted to tell you about Matlab, it would be good if you don't have it already, if you got it and familiarized yourself with it. So who already played with Matlab some? Most of you did. Who never touched it? Yeah. Okay, few of you. So the first thing you will need to do is to get Matlab. So you can, because already our first assignment will be Matlab warm-ups to sort of get some first interactions with Matlab. So you don't have to buy it. You could, I guess, if you wanted to, but we have free licenses which should be available for you. If you are online, you can try this link. There should be some information for licenses for you. I tried it and didn't work because it said that I'm not a student and it's only for students and only for students of some special courses, which EAS205 is one of those special courses, so you should have access to Matlab licenses. So the first thing you should do is to install it. I hope you could do it soon, so we can start with the homework soon. If it, maybe I think I used to issue the homeworks on Friday and have like a 1 week turnaround. They're usually not big, just like a small exercise. We'll start with the Matlab warm-ups. If there is some problem with your Matlab installation, or you just don't want to use your own computer or license for whatever reason, you can just use it in the sets labs. It should be already installed there. Okay, so please do this as your first homework, to just make sure that Matlab runs, that you can enter 1 + 1 and it computes 2. That's how you find out if the license is correct, because if the license is not working, it won't compute anything for you. And you can even go through Tintin's lecture on Matlab again and sort of try all these things by yourself to make sure it works the way you would expect it to work. All right, so I think if you have some problems with that, it's a good idea to contact the TAs or myself or Tintin. And I hope you could be all set up with Matlab on Friday, because I think on Friday would be a good time to fire off the first homework. That sounds good. First one will be just simple, just to do some simple Matlab programming. No fancy math or anything, just to get a little bit of a warm-up. Okay. If you have any questions, by the way, you can ask at any time, if you don't mind to be actually you won't be recorded, because it doesn't really pick up your voice, I think, anyway. Okay, project. So this is an applied course, so a big part of it are your own programming assignments, which will be done in Matlab, unless you are really like crazy to do it in some other language, but I would recommend to use Matlab because that's the easiest thing to do. We will start with the coordinate transformation, so that's a basic thing in robotics, but also in graphics if you want to do something like character animation, inverse kinematics, and those type of things. So we will go through it. It's only loosely related to linear algebra, but it's a nice application of basic matrix theory. So we will have homework on this, and it's incredibly useful thing to know. Splines, as I talked about before, how do you get nice smooth curves from non-smooth discrete input? Very useful in computer graphics, but also in other areas. The transform coding, the JPEG, MPEG. We will not do like a full JPEG or MPEG, but we will essentially go through the main idea, discrete cosine transformation. there is one homework on linear differential equations, which is essentially like a baby version of physics-based simulation. I'm teaching physics-based simulation in the spring semester, and this EAS205 is sort of like a good preparation for that, so you know the basic linear algebra for that. We will do the mini Google thing, the PageRank algorithm, and some examples of using PCA. So that's the way how you will actually remember what it is, by doing a project, the homework about it. Here is what students are often quite curious about, so what the grading is going to be. So the projects is the main part. Homework is almost the same as projects. Sometimes I will do some like mathy type homework, like sort of do some calculations on the paper, prove things, mostly as a preparation for the midterm and the final. It'll be like a more homeworky type of thing. And the projects, that means mostly programming projects in Matlab. Then we will do a midterm and a final. Those will be exams with just like you will be sitting here and solving some linear algebra problems on the paper. So that's sort of to complement the applied Matlab thing. Still, there is a focus, there is definitely emphasis on the applied stuff, on the Matlab programming, but you will also get to do like a little bit of proofs and maybe a little bit of computation on the paper, just to get more experience with linear algebra. And newly this year, I will give you an extra credit for class activity, like right here, right now. Or alternatively, if you are one of the silent, strong types who don't like to speak in public, like I used to be always shy to say something to the in the class, then now we have Piazza, the discussion forums, which you can all use to ask questions, but also to answer questions. So if somebody is quite active and answering questions about homeworks or projects on Piazza, I will also count it as activity, and you can get extra credit for that. So that extra credit might make the difference between like A and A+. That's what you are after. I don't think that the grades should be. Grades are traditionally very important to students, but they should not be overstated because when you will be eventually applying for jobs or for PhD studies, then the grades don't really matter all that much. What matters much more is what you actually know, what you have learned. As you know that at interviews, they usually don't ask what grade did you have, but they have you solve a problem, right? Quite often when I did interviews before for like game programming job, there is always like a little bit of linear algebra, at least like a basic vector type of operations, dot product and cross product and so on. So those are some of the skills we will go over here. All right, any questions? So we'll use Canvas. I suppose you are now familiar with Canvas, right? Somebody who never used it before. Okay, everybody knows Canvas. That's good. There used to be this Blackboard system before, but Canvas turns out to work much better. And I use it in this class mostly for handing out assignments and then collecting your solutions to the assignment. So all the projects and homeworks, I will just issue an assignment on Canvas. I guess you will all get a notification of that. There will be a due date. Typically, I think it's on Friday, and the due date is the following Friday, something like that, with some exceptions if there are some holidays and so on. And then you submit all your Matlab scripts and reports and so on for every homework. There will be, of course, a PDF document which will describe what you need to do and what you need to submit. And that's what you submit back on Canvas. I think we hopefully can start on Friday, as soon as everybody has successfully installed and ran Matlab and is able to compute 1 + 1 in Matlab. So stay tuned, you should get an update. You should all be on Canvas, I checked, that should be fine. If there are some special cases, like somebody signed up later or something like that and you are not, then please check that and tell me if there are any issues. So for discussions, as I mentioned already a little bit, we are using Piazza. It works so much better than emails because there is already like a 40 of you, and if everybody asks me a question, that's a disaster in the mailbox, especially if it's the same thing, right? So discussion forums which you can search. Well, I guess you know this better than me, or you grew up in this age of social networks and everything. So it's perfectly fine to ask questions related to the course homework. If you think there is some sort of problem with like the text of the homework, that something doesn't make sense, Piazza is the perfect place to ask. You can even ask anonymously there if you feel like I guess that could actually be useful, right? If you want to say, oh, I didn't get this in the class, and you don't want to basically admit that you don't want to feel responsible for giving your identity, that's fine. Just do that. Okay? It's better to provide anonymous feedback than no feedback, I guess. Yeah, last year at physics-based animation, some students have some sort of issues, but they didn't tell me until the evaluation when it was a little bit too late. So feel free to even post me anonymous things via Piazza if you feel like doing that. Of course, it's better to sign yourself. Okay, yeah, and as I said before, there's the 5% bonus credit. If somebody, usually there will be, your colleagues will be asking questions you might have already figured out. So if you have done that and you go through the Piazza forums and you answer their questions, that's a very nice thing to do, and that's why I introduced this extra reward credit to reward this activity. Okay. There's this usual boilerplate, but you need to be honest. So I guess the important thing is to say what is okay and what is not okay. So the assignments are to be done individually. We will not do any group projects in this class. It's a fairly basic course, and the assignments are also fairly basic. So the point is that you yourself practice it. And that's really the most important skill set. I don't really understand why somebody would be copying it from someone else, because then you are basically not doing it. You get the grade, and you might get a good grade, but you are sort of missing the point. So what is okay in terms of the rules? It's totally fine to talk about the homeworks and projects in general, but it's certainly not okay to just copy and paste someone else's code or solution. Okay, so asking questions is not only allowed but encouraged. Googling and copying solutions is not. That's standard, right? So here is an important thing. So what are the recommended readings? So the most important book is The Introduction to Linear Algebra by Gilbert Strang. That's an amazing book, and this course was designed more or less following the book. So if you read this book, you will most likely know almost everything that we will be covering. Sometimes we will go over some more things, but it can be only highly recommended. You don't really have to buy this book if you don't want to. All the materials that you will need will be discussed in class and then posted, recorded, and so on. But if you want a reference, or if you want to sort of look at the same material from a little bit different perspective, look at some more examples, if you want to do some practice problems for the midterm or the exam, this book has tons of that material. Gilbert Strang also has video lectures on OpenCourseWare at MIT, so they are also publicly available. You are very welcome to watch them. They are not exactly the same as the lectures I am doing here. Sometimes, well, I only watched a few, so I'll probably not comment on that. But if there is some topic you want to see it explained from a different perspective, then you can also check out Gilbert Strang's video lectures. Now, if you want to become like Matlab hackers, Matlab gurus, then you can, of course, get some Matlab book. it should not be necessary because we should only need the most basic functionality of Matlab. You shouldn't need anything super advanced. But of course, if you see Matlab being useful in your future careers, if you are interested in going into some applied type of things, I don't know, could be vision, robotics. Matlab is used like in lots of areas. So if you feel like learning Matlab would be useful for you, then you are welcome to do that. Again, this is not a Matlab course, so we will not really study Matlab per se, but if you want to look into that more, you're welcome to. All right. So I think that's it for the general introductory organizational matters, and we can jump into some real content. Unless I forgot something, unless you have some questions on organizational and general matters. Nope. So if you have some question later, you know where to ask, right? Ideally at the end. Okay, so let's start by this philosophical thing. As I was saying, there is multiple ways you can approach linear algebra from hardcore mathematical, starting from like axioms and then deriving theorems from those axioms. That's sort of how my linear algebra course was like. It's just like a bunch of theorems and proof and theorem and proof, and then how do you use it to solve real world problem? Go figure. So that's not how this course will look like. Here, I really like to stress out the sort of dual nature of linear algebra. You can often look at the things both in an algebraic and geometric perspective, which is something very cool because it's more like philosophical, I guess. The geometry is very good for intuition, visual intuition. The geometry. So first of all, I guess I should say. So what is algebra and what is geometry? So in general, algebra, and I mean abstract algebra. I don't mean like the high school level algebra where we just like manipulate expressions. Algebra is about studying sets with some special operations on them. Okay, so you know the vanilla examples like the set of real numbers, and the operation would be addition and multiplication. And now these operations, they have some special properties. They can be commutative, distributive, and so on. That's what algebra does, right? And linear algebra, you could easily approach this way. And we will do it to some level because it is good because it gives you some sort of formal, it gives it formal structure. So if you need to translate it to code, maybe later in your careers when you are actually working on some real world problems, maybe you will not want to be using Matlab anymore. Maybe like if you are in a company like Disney, chances are they don't really have Matlab on every computer, right? So you need to code it up in C++. And that's where the algebra comes handy because it gives you an idea about what the types are and what are the relationships. The operations sort of nicely map to functions in a in procedural programming languages. So that's a nice formalism. At the same time, it's good to have in your mind a geometric intuition about things. So what is geometry? Geometry in general is a science that studies shapes, sizes, lengths, angles, properties of the space and shapes in general. You can also create an axiomatic treatment of geometry. But what I think is really nice about geometry is that you can have this intuitive idea. And I learned this only much later after my first linear algebra course, that even if you need to like construct a rigorous mathematical proof, it's still probably best to start with your intuition. So some sort of imagine some sort of lines and points and projecting the point on a line or something like this. And from this intuition, it's often quite easy to construct the proof. And you will need to do some proofs, maybe not that complicated, some basic proofs in your midterms and final exams. Yeah, so I guess just to summarize this, my point was that better than to just like memorize the proof or start to try to analyze the proof, it's best to develop a geometric intuition, and in linear algebra you can often do that. Okay, so let's start with the very basics. Some of you might find this quite boring. This is like a 200 level course, so I start with really basic things and go over them slowly. So if it's too boring, you can then fast forward it. So I guess this is an illustration of the idea of geometric versus algebraic point of view. So if you look at vectors, we can sort of think about a vector as a little arrow going from the identity. And we can measure the coordinates of a vector by doing orthogonal projection on both of the axes. So this would be some 2 units. Here would be 1 unit. Right? And that's the Descartes coordinate system. So by the way, this idea of taking coordinates of vectors, that's a central theme of linear algebra, which we will formalize later. So a vector, so here is how you can look at vector as an arrow which has some coordinates with respect to some frame of reference. So here I chose some coordinate system. I chose an orthogonal coordinate system, these axes x and y, and I can find the coordinates of any vector with respect to these axes. And the tuples of numbers, they are called vectors, as you, I'm sure, know. So here is just a little bit of notation. By default, by vectors, I mean column vectors. You could also have row vectors, right? That would look like this. The interesting thing that both algebra and geometry, they don't really care about column as opposed to row vectors, but Matlab does, right? And computers actually do. So this is just a convention of how do you write it and how do you then deal with like matrix multiplication and so on, which is something we will get to later, but you probably already know some of that already. Okay, here is some notation. So R2 will mean a set of 2-dimensional vectors. So I'm not really formalizing these things. We will do more formalization later. So just sort of take it as a fact that R2 is a set of 2D vectors, so a set of these 2 tuples, pairs of numbers. So this would be an example of real vector because each of the components is a real number, right? But it wouldn't have to be necessarily real numbers. So you can build vector spaces not just over real numbers, but also over, for example, complex numbers. We will not do that much, even though lots of linear algebra libraries, they do support complex numbers too. But we'll be mostly focusing on the real case. In some cases, like when you are computing eigenvectors, it actually turns out it is quite natural to go to complex numbers, right? I assume everybody knows complex numbers. I do assume some basic math knowledge, but there is some problem, let me know, and I can explain that better. So what makes an algebra is giving the set of things. So in this case, the set would be set of 2-dimensional vectors, right? It's infinite, non-countable set. And what makes it an algebra is giving it operations, mathematical operations, algebraic operations. So these are the simplest operations you can think of. Multiplication by a scalar, right? Which means that I multiply every component of the vector by the scalar. So 5 times 1 gives me 5, 5 times 2 gives me 10. Vector addition or subtraction, it's equally trivial. That basically means that you go again by component, right? So you do 3 minus 5 is minus 2, 7 plus 2 is 9. The significance of this is that I have defined these operations on vectors, right? So if you want, I hope you are familiar with this notation. You can write it in like the mathematical functional notation like this. So the scalar multiplication would be something that consumes a scalar, a 2D vector, and returns a 2D vector. Are you all familiar with this notation? Yep, that's good. So what would be the signature, I guess, of this function of vector addition? Well, it would be R2 times R2 returns R2, right? So I guess if you were writing a function in Matlab or C++, it would be a function that would consume 2 vectors and return another vector. That's why I was saying the algebra is useful, because it sort of helps you think about how would you implement things when you are programming things for real. So this would be the algebraic version of the story. Yeah?
So the cross doesn't stand for multiplication in this case?
The cross?
No, in the notation.
Oh, so this cross, that stands for Cartesian product.
Okay.
You mean this cross?
Yeah.
Yes, yeah, right. So it's a little bit confusing. This cross is a different cross than here. So this cross here, it's good that you asked, because it's a little bit inconsistent. So this cross here, I'm hesitant to circle it or anything, because then it would get even more confusing. This cross here stands for scalar multiplication. Okay? This cross here stands for the Cartesian product of two sets. Okay, those are different operations. I would still stick with this notation, because this is fairly standard notation. Good that you asked. Yeah, thanks. Okay, so I was saying this is the algebraic version of this story. Okay, now let's see at the geometric picture of scalar multiplication and vector addition. So all very basic stuff, but it will give you an idea. So what is the geometric interpretation of scalar multiplication? Well, it's written here, right? So if I have a vector v and I multiply it by scalar a, so here I denote, actually maybe it's better to denote it by star. Maybe I could have done that here too. So like do it, give it a star. We are a little bit consistent. So here a is a scalar, v is a vector. And if a is in this case like 3 or something, then it means scaling the vector v by this scalar. Right? What happens if a is 0? I'll get a 0 vector, right? We will have the formal version of the formal definition of vector spaces, I think in the next lecture probably. And one of the axioms is that every vector space has a 0 vector in it. So this is sort of like your geometric interpretation of the scalar multiplication. So from here, you wouldn't really have to have any picture like this, right? It's just some sort of function that computes something, that consumes a number and a vector and returns me a different vector. But if you think about it this way, then scalar multiplication, that means scaling this arrow, right? That's your geometric interpretation. That's the simplest instance of the relationship between algebra and geometry. So what's the deal with vector addition if I'm adding two vectors, v plus w? So there is one, I guess one slightly non-intuitive thing about this diagram. So the thing is that vectors as a free vectors are denoted by arrows which I can freely move around. I'm sure you have probably seen this like license applied before, right? The vector w, it simply has just the two coordinates here. So I guess I could say that vector v has coordinates vx and vy. W has coordinates wx and wy. And this picture basically tells me visually that to do the vector addition, all I do is, so this would be my vx, right? And this thing, that would be the wx, right? The x component of v and x component of w. And if I put the arrows together like this, then this picture essentially encodes the idea that the x coordinate of the result will be vx plus wx, right? And the y coordinate of the result, by exactly the same logic, will be vy plus wy. Okay, so this is the vector w plus v. So again, think about it. This is actually interesting. Either you can think about it as adding the individual components, purely algebraic operation, or you can think about it as sort of stacking the arrows together, like going from here to here and putting another arrow here to here, and that's where I arrived. Like imagine like I start with a car or something here, then I drive here, then I drive this way, and the total a distance I traveled is represented by this vector w plus v. That's your geometric interpretation of vector addition. Okay? So in in 2D, it's all super easy, super intuitive, right? 2D, that's a plane. I can draw everything there. The power of linear algebra comes from the fact that it all works in higher dimensions. Higher dimensions are cool because you can imagine dimensions up to 3. If you can imagine 4 dimensions, then you are a semi-genius. And if you can visualize higher dimensional spaces intuitively, then you are like a superhuman, I think. I mean, there are some visualization techniques and so on, but the 2D space is just like this, 2D space. 3D space is essentially the space around us, even though some physicists might disagree, but let's leave that discussion for a different time. But imagine visualizing, having the geometric intuition about 4D and higher D space, it's more difficult. Nevertheless, linear algebra still works there, and your intuition might also work there. Because here's the cool thing. If you have a plane in like 100 dimensions or 1,000,000 dimensions, you can still apply your intuition from a 2D plane there. Okay, so the notation here is fairly standard, right? So R2 obviously gets generalized to Rn if we go to n dimensions, where n can be arbitrary integer greater than 1. So this would be an example of a 3-dimensional linear space, 6-dimensional. And the cool thing about Matlab is that it's quite efficient even in high dimensions. So you can easily go to like thousands of dimensions. And often you actually often need that, right? If you are like doing something like audio or images, as we talked about audio and image compression, then your signal, you often look at it as a one single vector, right? Depending on what is your sampling rate, that can easily have tens of thousands of dimensions or even millions of dimensions. So let's look at another operation we can do with vectors, and that's the inner product. So you probably all know inner product, right? So I think this will be just a recap. So let me try to go a little bit quicker here. So the inner product, so what is the signature of inner product? If I was gonna write it using the Cartesian product notation, what is inner product? So if I'm in R2, let's stick with R2 for this slide, then inner product is an operation which comes in one vector, another vector, and gives me what? Sorry? R, yeah, it's just a scalar, yes. So it takes two vectors and produces a number. And how the number is computed? Well, I just take the first component and the second component, multiply them together and sum them together. The sum is how we sort of reduce it from all these dimensions to just one dimension, or from 2 dimensions to 1 dimension. So here are some trivial examples. If you want to do inner product of these vectors, you compute 1 times 3 plus 2 times 4 and get 11. If there are negative numbers, that should not confuse you, or zeros, right? There could be whatever real numbers. If it's a real vector space, so 3 times 2 plus minus 5 times 1, that would be 1. And some of the like midterm exams, you might need to do some computations like this, but I hope that should not be a problem. So inner product in higher dimension works pretty much the same way. You just generalize it from 2 to n. So if you have n-dimensional vectors, it means they have n components. The inner product now is a function Rn, still returning a scalar. So here is always 1. Sometimes you could write the scalars as R1, whatever, right? It's like something to the power of 1 is still the same thing. And this is just a notation of the individual components of the vector v and vector w. You must have seen this before, I suppose. So in all cases, no matter how many dimensions, no matter how big n this was, it returns just a single scalar. And the scalar tells us something about the relationship of the vectors v and w. That's what I will describe in the following. So here is an example of an inner product for two 3D vectors. And just as I said, you just take the individual coordinates, 1 times 3 plus 2 times 4 plus 5 times minus 1, sum it all together, and that's the result. That's an inner product, which is incredibly important concept in linear algebra. And it's closely related to the concept of Euclidean norm. So the Euclidean norm squared is essentially the inner product of a vector with itself. So that's a special case, right? Because here I define the inner product for v dot w, but nothing prevents me for just using it on the v, for taking v in place of w, right? So doing v dot v, which means that I am taking the interval coordinates and squaring them and summing them together, right? So if I do v inner product v, by the way, dot product and inner product, that means the same thing. Inner product and dot product, those are synonyms. So v dot v, v inner product v, that's just the sum of squares of the individual components. And this is the square of the length of the vector. This is called the Euclidean norm after I take the square root of this. So if I don't take the square root, then we talk about squared Euclidean norm, and if I take the square root, then I get the length of the vector. That's the Pythagorean theorem, right? Here is a 2D illustration of that. I think you must have this at high school probably already, right? So if this is a vector with components x and y, the length of this vector, that's the square root of x squared plus y squared. Okay. So let's look at some properties. So let's sort of look at the algebraic interpretation of inner products. So first thing you can realize that inner product is commutative, right? And there's a very easy way to prove it formally. Again, even though I'm not pretending to sort of do like mathematically rigorous anything, sometimes it's useful to think about how to prove things, especially if it's easy to come up with that proof. So here it's trivial, right? Because if I do v inner product w, then by definition it's the sum of vi wi. And if I do the inner product of w with v, so just swap the roles of v and w, then I get w and v. But these are scalars, so they are commutative. So these two things definitely are equal. That's my proof. So inner product is commutative, which we can write this way. Okay, quite. Yeah?
Do you have a geometric interpretation of inner product?
Yes, there will be one. It's coming. It takes a little bit of legwork to get there, and this is we are actually starting to sort of build up to it. Sometimes you have to work to get your geometric interpretation. Sometimes it doesn't come just like this. Sometimes you have to sort of figure out some things, and these are so we are getting there. Yeah, thanks. Hopefully today. So distributivity of inner product with respect to scalar multiplication. So what does it mean? It means that if I do the dot product of a vector v and a vector w, which has been scalarly multiplied by a scalar alpha, so here alpha is a real number. So the distributivity says it doesn't matter if I first multiply the w by alpha and then do the dot product, or if I first do the dot product and then multiply by alpha. That's what the distributivity means, that I can essentially pull out this alpha out of this expression, put it here. Okay. How do I prove it? Again, very trivial, right? Just applying the definition of inner product. So by definition, this inner product is this. And of course, the standard real number multiplication is distributive. You know that I can pull out the alpha out of the sum, and that gives me exactly this. easy breezy proof, right? But it's a proof, it's fine. It's a good sort of to understand the concept of a proof, especially as I will want you to prove some things for your midterm and final exam. So here is another property of the inner product. This is distributivity with respect to vector addition. So what it means is, again, it doesn't matter if I first add v plus w and then do dot product with u. I get the same thing as if I first do the dot product u dot v, u dot w, and then add them together, right? Because it would make sense to think about it in terms of like a computational diagram, right? Like that. Here you know how the priority works, right? Certainly, the priority of multiplication is higher than that of addition. So this means I first do the addition, then do the dot product. Here, I first do the dot products, then do the addition. And the distributivity says that these two things are the same. Again, the proof very, very simple, right? You just write it out. You have the distributivity here, so you see the two dot products. Is it too simple or too fast when I explain it like this? I'm curious. Are you like bored, or is it, or I'm going too fast? It's good. Okay. And this is just the sort of introduction thing. It will get more interesting, I promise you, later on. Okay, so here some more interesting, or it's starting to get slightly more interesting. Okay, so if we apply the distributivity twice, and why I'm doing all this, I'm sort of building up to exactly what you asked about, the geometric interpretation of inner product. But let's take the baby steps. So let's first figure out what is the dot product of a plus b and c plus d. So or a, b, c, and d, they are vectors of the same dimension, otherwise it wouldn't work, right? That's the important thing to keep in mind, that you cannot really add vectors of different dimensions. It would be undefined. You would get an error in Matlab or something like that. The same way you cannot do a dot product of vectors of different dimensions, right? And if you have an expression like this, we can apply the distributive property twice, right? So first we can distribute with respect to the first sum. So we see that this is the same as a dot c plus d plus b dot c plus d. And then we can apply the distributive property again. So this would be a times c plus a times d plus b times c plus b times d, where by times I mean the dot product. Okay? So this is just applying the distributivity twice, right? First, this is, or three times if you will, right? This is one, this is second, this is third. And again, I can apply it. I can just say that c and d is again a and b. I can just apply the dot product of a plus b to itself. And I get a slightly more interesting formula. So this basically, I just substitute for c and d, I substitute a and b, right? So this means this norm squared, remember, you should always keep in mind norm squared means dot product of the vector with itself, right? Every time you see x norm squared means x dot x. That's a definition. That's something you absolutely must remember if you don't remember it already. So here I just apply the distributivity as many times as I need. And here is an interesting thing. Remember the commutativity? You put all these things together. That's the beauty of proof, right? You put all lots of simple things one on top of each other, and then eventually you get something interesting. Slightly interesting in this case. So here I can use the commutativity, right? So I know that b dot a is the same as a dot b. So I have it here twice. Here is one a dot b and another a dot b, right? So they are there twice. And I can apply this identity again. So I can just say this is my square norm. And this is the formula. This formula might remind you something you know for real numbers, right? You know probably from high school that this is a formula for real numbers. This is essentially the analog of this formula for dot product and vectors. All right. Now we will bring in the concept of cosine. So let's jump in there. The cosine rule. Let's stare at it for a second. So I guess I could start, you can ignore this. Let me just explain the cosine rule in a simpler way first. So if I have a triangle, so what does the cosine rule say? Do you remember that one? I would probably have to like do a little bit of Wikipedia to refresh. Huh? Yeah, I'll also post the slides. So, I mean, you will have the entire recording, which I think is better than the slides, but I also post the slides on Canvas. Yeah. So if I have a triangle and the length of the edges are A, B, and C, and I know also the angle alpha, then there is a relationship between these four numbers, and that's the cosine rule. The cosine rule says that c squared is a squared plus b squared minus 2ab cosine of alpha. That's for a 2D triangle, even though, of course, it would work in any other dimension as well. So let's see how we can apply this to learn something about the dot product. That's essentially working on the answer for your question. What is the geometric interpretation of dot product? So first, let's apply this identity on the previous slide. Let's just say that the b is minus b, right? So what changes if instead of b I take minus b? So a minus b. Well, nothing changes here, right? Because those are squares, so they consume the minus. But a dot b is gonna be with minus, right? So this sign flips, and that's exactly what I have here. So if I take the square norm of v minus w, I get this. Is that clear? Good. And now we can use the cosine rule. So here is how it maps to the triangle. So here is my vector v, here is my vector w, and this would be the v minus w. Right, before we had the same picture where we were adding this vector with this vector and we got v. So clearly if you want to go the other way around, you want to subtract w from v, you get this vector. Okay? And here you can see, if here I can apply the cosine rule to it, because if I take the square norm of the vector v minus w, then I have nothing but c squared, right? And the length, this length squared is the norm squared of v, so that would be my a squared. W squared would be my b, and what I have to put there is the length of v times the length of w, that's this, times the cosine of the angle theta, that's this angle right here. So that's basically applying the cosine rule, which I wrote for a general triangle, to this particular triangle, where I wrote the sides of the triangle as vectors. Okay? Is that clear? So here comes the interesting, here is the interesting part. So this is the same as this, right? Which means that these two things must be equal, right? That these things are equal. Yeah?
Oh, sorry, what is this invertible lines without the square sign?
Oh, this norm?
Yeah.
Oh yeah, sorry. So I said here that the norm with the square is this. So if I write it without the square, that means I took the square root of that.
Oh.
Okay, so this is the norm. With the square, it's the square norm. So this means just the length of the vector. Okay? So simply put
Without the direction?
it forgets the direction, so the length is just a scalar. It's just a real number.
Oh,
Okay? And it tells me how long this is.
okay.
So for example, if I have a vector 1, 2, let's say that x is 1, 2, what is the length of x?
Root two.
Hmm?
Root two.
Square root of what?
Yeah.
Any other opinions? Square root of 5, exactly. Because I take 1 plus 2 squared, that's 5 square root of 5, right? So 2.1 or 2.2, something like that. That's the length. That's what I mean here. And this is just the length squared, or norm squared. Okay? So here's the cool thing. So these two things are equal because this is the same as this. So obviously these two things must be equal too, because this was just a different rewriting of these expressions. This was using massaging the dot product. This was using the cosine rule. So these two things must be equal. So what does that mean? Well, these two things cancel out, right? So this thing here is the same as, okay, get me go a little bit slow. Is this the same as here? This square norm of W appears here too. So from this, I see that there is no other possibility than minus 2V dot W must be exactly the same thing as minus 2 the norm of V times the norm of W. So this times is just a scalar, real number times real number. In this case, it means the dot product. Again, it's a little bit of incorrect notation or inconsistent notation, but that's okay. I have to live with that. And of course, I can just divide by minus 2, right? And from this, oh, and that was the cosine, sorry. That was this time cosine theta. And from this, if I divide by minus 2, I just see that the dot product of V and W is equal to the norm of V times norm of W times cosine of theta. Okay? And that means that we almost have this is the key to the geometric interpretation of the dot product. Because it tells us that the dot product is intimately related to the cosine of the angle between the two vectors. So let's take a look at it in a little bit more detail here. Actually, let me copy the formula there. So I said before that V dot W is the norm of V times the norm of W times the cosine of theta. How does cosine look like? Do you remember cosine? So cosine starts at 0. It starts at 1. Then it drops down to 0 and then goes to minus 1, right? So when I'm at pi half, I'm at 0. And when I get all the way to pi, I go down to minus 1, right? That's how cosine looks like. Now here's the cool thing. The norm of V and norm of W, those are lengths of the vectors. So they are always non-negative numbers, right? At worst, it can be 0. There's no way it could be below 0, right? So the sign of the dot product is entirely determined by the sign of the cosine of theta, right? And the sign of the cosine of theta is exactly determined by what the theta is, because if the angle between the two vectors is less than 90 degrees, less than pi half in radians, that means that the sign of the dot product is positive, right? That means that the vectors are sort of close together, intuitively, geometrically, okay? If the dot product is exactly 0, that's the special case where this theta is exactly how much? 90 degrees. And the last case, if the dot product is negative, it means that the theta must be more than 90 degrees. It's between 90 and 180 degrees. Slightly tricky question, can I go beyond 180 degrees? Like what if I rotated this W to like here, and then I was claiming, okay, here is like 200 degrees. That's not how it works, right? Because the shortest angle applies. So in this case, the dot product would still be negative, and it would correspond to this angle between the two vectors. So the angle is always between 0 and 180 degrees between the two vectors. Okay? And this works not just for 2D vectors, but also for vectors in arbitrary dimension. For 2D vectors, you can reason about it. What does it mean, right? For vectors in arbitrary dimensions, it's a little more abstract, but the idea is still the same. The special case is if you do vector with itself, right? In that case, the angle theta is 0, obviously, right? So the inner product, essentially, you could think about it, it measures the length of the two vectors, and you can think about it as similarity. In how much similar direction are the two vectors pointing? And that's sort of cool, because if you have million-dimensional vectors, which sort of, I used it before when I was working on some program that was processing texts. You have a text as a bag of words, and you represent it as a vector, which can have a million dimensions. And if you want to compare how two articles are similar, you can just use the dot product, and sort of gives you a measure of similarity. Or maybe a better example would be images. Imagine you have a 256 monochrome images. So this would be 65,000 dimensional, roughly 65533 dimensional vectors. If you compute the dot product between the two images, it sort of tells you how similar or dissimilar the images are in this cosine theta interpretation of similarity. All right. So this special, so we will need to end at 5:50, right? That's the convention here, and it's also getting late. But let me just mention one more thing, and that's orthogonality. So that's the special case here, where the dot product is exactly 0. Yeah, question?
So more similar doesn't mean less number, right?
Less number.
Like the less result of the dot product.
Right.
Because here 0 is with like 90-degree vectors.
Correct. That means that they are not really very similar. I mean, the similarity, it's not really rigorously defined similarity, and you probably could think about different, so I didn't mean to confuse you by the idea of similarity. Now what I meant is that if the vectors are units, so both lengths are 1, and you get a dot product which is close to 1, that you are almost certain that the vectors are almost the same, right? Because if the vectors are like, if it's a case like this, one vector is like this and the other one is almost the same, then you will get a theta close to 0 degrees. Yeah? We will elaborate on this a little bit more later on. Okay, I see that you are already packing up, so we will discuss orthogonality and Cauchy-Schwarz inequality, I guess next Monday, right? All right. Okay, thank you.